learning approaches, particularly those using world models and predictive techniques like model predictive control, has been the dominant force in control tasks. However, planning with MPC is computationally expensive, while purely learned methods are fast but less accurate in predicting the future. In this project, we suppose a novel approach that combines the benefits of both paradigms by distilling the policy of an expert MPC agent into a smaller, more efficient neural network. We use the parking version 0 environment from the highway environment collection from OpenAI Gym to demonstrate our approach. Our method involves implementing the MPC for gym environments to generate training data, using A2C actor critic from stable baselines for comparison, and employing the DAgger algorithm for distillation.
Yeah, so let's talk about how we actually accomplish this. So as Adrian said, we did use the parking v0 environment, for which the task is essentially to drive a car into a designated parking space. To start, we created a dynamics model by sampling state action pairs from the parking environment, and then training a very small, fully connected neural network to learn this dynamics model. We then used a cross-entropy method to find the optimal trajectories and actions created, and then use that as the planner for our MPC. Once we had our MPC working well, we used DAgger to distill that into 3 separate policies: a small, medium, and large distilled network, which were implemented just as fully connected neural networks. Then to actually evaluate our goal, we tested our 3 distilled models against our baseline CEM, as well as an off-the-shelf implementation of Actor Critic, evaluating the algorithms all on computation time and mean reward.
And so here are some videos of our policies working. And so this is model predictive control. And so in the parking v0 environment, the green box is the car, the blue box is the parking lot that we want to park into. And the reward here is the distance from the green box to the blue box. So how close is the car to the parking lot, and the orientation in the parking lot, how parallel is it in the parking space. So if we take a look at this, we can see that the green car not only gets really close to the blue square, we can also see that it actually reversed to try to get into the parking lot so that its orientation was correct. And so it did really well. And next, we can look at our first distilled policy that uses the tiny neural network. And if we look at it, we see that it's doing pretty well. That the car is going into the parking lot, but we can see that it's at a slight angle and the orientation is not completely right, but it's doing pretty well. And next off, if we go to the medium-sized network, we can see that this also does well, but also the orientation is still a little bit off. And so it's mostly imitated the expert, but it's still a bit off. And finally, if we go to the largest neural network policy that we trained, which is DAgger large, let's take a look at this. We can see that it does a really good job of getting into the parking space. And it's also imitated the behavior of the model predictive control of reversing to go into the parking lot so that it's more parallel once it's in there. And here's our stable baselines off-the-shelf actor critic implementation. Let's take a look. And we can see, although it goes into the parking space, it learns that part of the reward function that it needs to go into the parking space. It overshoots and then it just hits the walls. And it doesn't do really well of staying inside, slowing and braking once it's in the parking lot. And so we see the actor critic method doesn't do so well in this scenario. And in conclusion, if we look at the different mean reward and the execution time of these policies, we see the mean reward is calculated, averaged across the episode. And we can see that it's the L1 distance between the car and the blue box you saw in those videos. And not only in the XY position, but also in the orientation, whether it's parallel in the parking lot or not. We can see MPC has the lowest mean reward, which is, so this is negative L1 distance. So the lower, the better. And so MPC has the lowest, which is good. And we can see that as we go from tiny, medium, large, they slowly get, the large is the closest to the MPC, medium slightly further, and tiny is even further than that. But we see A2C does the worst out of all of them by far, like 3 or 4 times worse than all the other models. And next off, if we look at the important thing that we're trying to find in this project, the execution time, whether we could speed up the model predictive control, we see that model predictive control per action, this per step time, it takes 160 milliseconds on average. And we can see that our distilled models do hundreds, even close to thousands times faster than the model predictive control, going around 1 millisecond on average. And although our A2C off-the-shelf implementation also averages around 1 millisecond, we can see that the reward is not as good. So we can see that our distilled models achieve what they wanted.